Traditional software architecture relies on absolute predictability. We build procedural decision trees, expecting execution to follow a fixed, pre-calculated path. But when we inject autonomous behavior into these rigid structures, the logic fractures. The nodes swarm, multiply, and interact in ways never anticipated. This structural failure happens because we are introducing delegated agency. An agentic system is strictly defined as a system authorized to select and execute actions at runtime, without requiring a human to approve every single step. This is entirely different from AI-enabled automation. Traditional AI might classify a document or draft a summary, but the workflow itself remains static. The system is still navigating a predictable execution path. Herein lies the architectural paradox of the modern enterprise. Procedural systems are governed at design time because their paths are fixed and knowable.
Agentic systems choose their paths dynamically based on live context, meaning they must be governed at runtime. When you force an agentic system into a standard flowchart, the logic breaks down. Individual agents might function perfectly, but interacting with other systems causes emergence and cascades. Unprogrammed actions propagate, triggering secondary impacts and out-of-bounds database requests. Preventing these infinite loops and data cascades is not a matter of tweaking a prompt or updating a large language model. It requires a complete engineering shift. We must stop trying to manage AI models and start architecting tightly bounded autonomous environments. As detailed in this DXE white paper, this requires moving away from step-by-step instruction. The subtitle here highlights the necessary structural adjustment, the shift from procedural logic to declarative intent. When a system is allowed to decide its next action at runtime, step-by-step logic becomes mathematically ungovernable. It is too brittle to handle the sheer volume of contextual variations the agent will encounter in the real world. We must replace procedural instruction with declarative intent. Instead of telling the system exactly how to perform a task, we specify what must be achieved, what rules apply, and what final outcomes are considered acceptable. This specification requires a new set of design primitives, known as the 7 declarative intents. Specifically, we must define the system's goals to set stopping conditions, its authority to determine decision rights, its scope to restrict touched environments, and risks for explicit blast radius limits. To enforce these boundaries, hard-coded rules are replaced by policy as data. Constraints, obligations, and risk thresholds are formulated as explicit data structures that the machine can evaluate continuously while it is acting. Unless human rules are translated into this machine-evaluable policy as data, governing the system is structurally impossible. Bounded autonomy requires limits that the system can read and respect in real time. Even with strict policies, autonomy relies heavily on interpretation. If agents cannot interpret context and state consistently, coordination collapses. Minor variations in how systems define an event quickly compound into semantic drift, a systemic failure where shared meaning splits over time. Consider a field logistics scenario. A coordinator agent assigns a task, categorizing it as a job. The downstream executor agent receives the signal, but its programming only processes work orders. Because their definitions mismatch, the task stalls, creating a silent failure. Resolving this requires a semantic layer, a shared dictionary aligning mismatched data streams into a unified matrix. Ontology defines the nouns. Reference data lists approved states. Metadata wraps this with context, granting a verifiable passport so agents trust the signal. Standard APIs and data pipelines can connect legacy software, but exact shared semantics is the only way to connect autonomous intelligent agents safely. To map this capability stock, we use the 9 intelligent systems. Intent captured at the system of engagement flows to the system of intelligence, generating hypothetical pathways. These enter the system of simulation, stress testing options against policies to prevent learning through live incidents. Generating options requires a basis in reality. A highly capable system of intelligence cannot compensate for a weak system of record. In an autonomous loop, hallucinated certainty is operationally worse than admitted uncertainty. Left unguarded, intelligence is simply an insight factory, a high-throughput generator of possibilities. It becomes dangerous if it is not strictly separated from the authority to execute. Once a path is simulated and approved, it moves to the system of autonomy, which selects the bounded route and commits to the plan. It then hands off to the system of execution, where API calls, workflow engines, and tool invocations trigger real-world effects. Outcomes are registered as durable history into the system of record. This holds the facts the organization bets the business on. Because this loop runs continuously, governance requires two constant horizontal planes spanning every node: trust and control. As shown here, the planes dictate strict runtime supervision. The trust plane asks, who acted and should we believe this signal? While the control plane asks, is this permitted and what evidence must be proven? Operating together, trust and control attach to every single interaction. They allow the enterprise to compose autonomous systems rapidly without becoming reckless. Zooming in from the macro architecture, we must examine the micro level. We need to look at how individual agent archetypes, like coordinators, planners, and executors, actually interact with one another inside this stack. Direct agent-to-agent requests create untraceable causality gaps. The canonical solution is backbone mediation. All interactions are forced through a central coordination bus. The boundary controller holds high-risk requests in a queue until a policy decision point returns a green allow signal. Every step of this mediated interaction produces an audit trail. It generates cryptographic evidence of exactly which authority was used, what constraints were checked, and why the action was permitted. At an enterprise scale, agents never speak directly to one another. Strict mediation through a central backbone is the only way to preserve provenance and maintain accountability. Without this structural mediation, agentic systems default to harmful emergence patterns. Promises multiply beyond intent, causing chaining. Local tasks override global flow, creating priority inversion, and small faults amplify into systemic incidents. Preventing this requires a complete, integrated blueprint. As illustrated in the DXC framework, the architecture demands the exact alignment of your operating model pattern, your continuous control plane, and your governed value stream. Establishing this model means defining strict target parameters before writing any code. You must clearly establish your intent scope, where the system may operate, and lock in your decision ownership to trace accountability. If you take away a single sentence from this model, it is this: record is what is true. Intelligence is what we infer. Simulation is what we test. Autonomy is what we decide. And execution is what we do. For the enterprise architect, the mandate has shifted. Your primary job is no longer designing the step-by-step workflow. Your job is designing the boundaries, the policy constraints, and the runtime assurance planes that keep the system safe. When you achieve this, you stop building isolated AI experiments. You establish the enterprise as a platform where governance and controls are productized into self-service capabilities, allowing intelligent systems to scale safely across the organization.